Hey guys, welcome back to the channel. Today we're going to do a deep dive into everything you need to know about dynamic programming. So first, as always, let's start with this Fibonacci sequence, which is a very common example when it comes to dynamic programming. And the Fibonacci sequence is pretty straightforward. All it says is it's a sequence of numbers, say f of n, where for each index, okay, we know the first two, 1 and 1, okay, these are our base cases. Then every other index that comes after the first two is just a sum of the previous two, meaning the next number is going to be 1 plus 1, which is 2. Next number is going to be 1 plus 2, which is 3. Next number is going to be 2 plus 3, which is 5. Next number is going to be 3 plus 5, which is 8. And it goes on and on and on forever. Okay, so let's go ahead and see. Okay, so this is the first index, index 1. This is index 2. This is index 3. This is index 4, 5, 6, and on. Okay, so this is pretty straightforward. So let's go ahead and deep dive into it. So the first method we're going to use to solve the Fibonacci sequence issue, it's, well, not an issue, the problem, is called the recursive method. Okay, there's different ways to solve it, but this is actually one of the most common ways. Okay, I hope I spelled it correctly. Spelling is not my strongest stuff. But anyways, I'll define a function called def Fibonacci. Fib. Let's call it fibrec of n. Okay. So this is to keep a rec. This is the rec is for recursive. Okay. For now, let's say pass. And let's also go ahead and create a driver code just to call this function, just so we can see what's going on when we call it. I'm just gonna comment this driver code. Okay, and I'm just gonna say n equals 5. Okay, now let's print fib rec of n. Okay, so if we run this guys now, it shouldn't do anything because we're passing right here, so it should just not do nothing. And then run this guy, nothing. Okay, good. So now Fibonacci, like we said, the first two numbers are our base case. We know it's 1 and 1, and every other number after that is the sum of the previous two numbers. So it's just simple. Let's say if n is less than or equal to 2, okay, it's our base case. We know results. It's gonna be 1, okay? Else result is gonna be the recursive call to the Fibonacci function. So it's just gonna be result of fib of n minus 1 plus fib of n minus 2. And then once this is calculated, once we're done with this step, we're gonna return what? We want to return the result. Okay, this should be straightforward. Now let's go ahead and test it. So as we said, fib of 5 is 5, so we should expect to get 5 in here. Bam. So we know it works. Okay, so this is the first method. Okay, but while this method works, it's not the best, and here's why. So we're asking, let me go ahead and choose black. Okay, so we're looking for fib of 5. Okay, recursive call is going to break it into 2, okay, because it's just fib of 4 plus fib of 3. Okay, now each of these legs can break into 2 one more time. So this guy is just fib of 3 and fib of 2. Okay, fib of 2 is one of our base cases. We've hit it. It's 1. We know it is our base case, so that's good. But this guy is not at a base case yet. We can break it into 2. He's fib of 2 and fib of 1. Now we're at both base cases. Okay, now for this guy can be broken into 2, just like this guy, fib of 1, fib of 2. So the problem with this recursive method is every time we calculate, for instance, let's trace one of the legs. So from this leg down here, this is one leg. Okay, we're gonna have to do these calculations each, but we've done this calculation here, so the base case is 1. We also have to do it here, 1. We also have to do it here and here, which doesn't save time. As far as time complexity goes, this function, since it has a height of n, because we passed in fib of n is 5, a height of n, so the time complexity is big O of 2n. This is because each leg breaks into 2 branches. Think of it like a tree that breaks into 2, and it has a height of n. We can simplify this problem to where we get a time complexity of big O of just n, which is a linear time complexity compared to this quadratic. We prefer linear. If you can get the time complexity lower, it's always better. And here's how we do it. We do it using something we call memoization. And let's put it to code now. And this is called memoization, not memorization, so don't confuse those two. So I'm just gonna go ahead and copy this guy and paste him in here and call it fib memo. Okay, so the first step with fib memo is we want to pass in a second item which keeps track of the numbers we've already seen, so we don't calculate it. So we'll use a dictionary in this case, memo, and set it on empty dictionary. Okay, so now we're gonna say if n is in memo. Okay, if n is in memo, what do we want to do? We just want to return. We're saying if this key n is in the dictionary, let's return the value at that key, because that's the Fibonacci number we need. Okay, however, if he's not in there, okay, now we have to do the calculation. If he's not in there, then we're going to say memo of n is going to be equal to this calculation we're doing. But don't forget, it's called fib memo now, not feedback. So let's call him recursively on himself. Okay, and then let's just set him equal results and return results. So that way we're always saving him. Whenever we see a number for the first time, we're saving it. This method is much better. Let's go ahead and print. Let's call him fib memo of n. Keep in mind that the second parameter in this function is memo is optional because we have him initialized on empty dictionary. Let's go ahead and run this, and now run this. Okay, we have them correctly. I want to tell you that this second method is a lot faster than the first method, but don't take my word for it. Towards the end of this video, I'm going to show you how and why it's a lot faster. Okay, so now thinking of this, you might think, hey, why creating a dictionary key value pairs? How about we just use a simple array to keep track of this, so that way we don't need to keep a dictionary. And here's how a simple array might work. Okay, with a simple array, all we have to do is we know the base case. We've established f of n, just like we know the base case is 1 and 1. Okay, this is the first index and the second index. Okay, however, the next guy is just the previous sum of the previous two, so we could just use an array to keep track of this and not need a dictionary. Okay, and let's see if an array keeping track of our memorization is, well, not memorization in this case, just keeping track of the fib sequence is better than a dictionary. So we call this method the bottom-up approach, and let's see. Okay, call this bottom-up, bottoms up. Okay, so let's define the function def fib but. Okay, let's call it but up. Okay, and it takes in n. That's all it takes in. Okay, so now the first statement, just like before. Okay, if n is less than 2, we just want result to be equal 1. It's really that simple. Okay, however, once we come outside of this if statement, now we want to initialize an array, or in this case I'm going to call it a list to keep track of what's going on. So I'm going to call it fib list and set him equal to, I'm going to set him equal to zeros times n plus 1. And I'm going to show you why the n plus 1 in this case. It's because arrays are 0 based. The first index of an array is a 0 based. So let me go ahead and print this. First index of our array is 0. So we have to keep track of it. Just to show you guys what I'm doing. Let's go ahead and call this function. So we call it fib bottom up, and we have n equal 5. So this should print 6 zeros once I call this function. Okay, so let's go ahead and run this, and let's run this. Yeah, 1 2 3 4 5 6. We have 6 zeros printed. Okay, this is because this will be our 0 index, then every other guy will be the Fibonacci sequence. So this will be our index 1, index 2, index 3, and on, just kind of like we have it here. So pretty much all we're doing is we're just adding a 0 here for our 0 index, and then everyone else is just the sum we know and love. So now once we have this, so what do we want to do? We want to initialize the first guy in the list. So we want to say fib list of 1, okay, not 0, we're going to leave 0, and fib list of 2. Okay, what is it equal to? Is equal to 1. just like our base case said. Now we want to iterate from the third index. So for I in range 3, again, because we already have the 0 index 0, we have 1 and 1 for the first and second, so we want to start from the third index and go forward. Okay, from the range 3, we want to iterate to n plus 1. Keep in mind the range function is inclusive of the lower bound but exclusive of the upper bound. That's why we're going to n plus 1, so we can get to n. So what do we want to do? We want to say fifth list of I. Okay, so the ith index is just gonna be, again, the same formula we've always used for the Fibonacci sequence. I minus 1 index plus I minus 2. Okay, so once we calculate this, we just want to say result, or we don't have to, let's use the result variable just so we stay consistent, but typically we don't have to. Result equals to fib of I. Okay, and guess what we want to do? We want to return the whole array result. Okay, let's run this one more time just to make sure it works. Good. 5, 5, 5 for all 3 of the functions we created. So now this doesn't tell us how fast they run. So now let's do the timing analysis and see who is the fastest, who is the best, who is the LeBron James of functions right here, who's the Michael Jordan, the Steph Curry of functions right here. This notebook I'm using to write Python code is called Google Collab, and it provides us a function called timeIt. Okay, so this timeIt can be used to time how long a function executes. So what it does under the hood is it runs the function 1,000 times, 1 or 10,000 times for various inputs, and sees and takes the average of how the function performs. So let's go ahead and run this and see who takes the longest and who takes the shortest. So you see, for n equals 5, which is a relatively small n, fibrec using the recursive method by itself took 1.2 microseconds. Not bad. Fibmemo, however, took 156 nanoseconds, which is literally almost 10 million times faster than this guy. 10,000 times faster, I'm sorry, not 10 million, than this guy, because this is 0.1 micro. If you go from nano to micro, it's 0.1, and then, yep. So this is about, actually it's 10, it's just 10 times, I'm tripping. This is just 10 times faster. And then this guy, I'll say he's about the same speed as this guy. So this is the fastest, this is the fastest, Memo is the fastest. These two are about roughly the same speed. So now let's start to see what happens as n scales higher. So let me just go ahead and take a, oh no, I don't need to snip it. Let's just go ahead and copy this code, create a new block. Let's copy him right here. Let's change n to 35 and see what happens. We can see for n equals 35, okay, the first guy, fibrec, runs in 2 seconds. The second guy runs in still roughly the same as he did before, 1.56. In fact, it even runs slightly faster, to be honest, than it did before for higher end. So this guy is just so perfect. He's just so perfect. But anyway, for this guy runs in 6 microseconds. So now for as n scales up, this guy starts to be better. He starts to be better than the first guy. So FibBottomUp starts to be better than fibrec. So now let's do a much bigger n. Let's say n equals 50. So the process was taking too long, if you can see the time now. So I'm gonna kill it right now because it's still, see the green arrow is still stuck on this first one for a while now. So I'm just gonna kill it just because n is so high. So calculating fib of 50 is gonna take forever. However, I'm gonna comment this guy out and run him with these 2 methods and see what happens. It's still gonna take a while, but it should be a lot faster for this guy most likely. Bam. So memorization is done in what, 3 seconds. Now this guy too is done. Let's compare both of them. Bam. You see how fast it is for these two? However, for this guy, I estimate it's gonna take about an hour for this recursive method to complete. So that's it for the video, guys. I hope it was helpful, and I'll see you guys on the next one.